Okay, walking around, I've seen one student today get number 30 right. Okay, and none of you really got 29 right either. So let's go back to this. We talked about this yesterday. When you're asked if two events are independent or not, okay, really there's only two things that we can take a look at now. You should always ask yourself this question. This is what we talked about yesterday. If knowing one event happens, does it change the probability that the next event would happen? That's the question you should have asked yourself on number 29. On number 29, the probabilities were 26% that they had 4 years of college, and then the probability that they were a laborer was 16%. And they asked you, do you think these events are dependent or independent? You then ask yourself this question. This is what should be on your paper right now. So let's think this through for a little bit. These are the probabilities that these people are these things. However, if you know the person you got went to 4 years of college and got a degree, do you think that changes the probability that they're a laborer off of 16%? Either way. Or you can say it the other way. If you know someone's a laborer, does that change, you think, the probability that they completed 4 years of college? And I'm starting to see some nods out there. Yeah, I think so. I think there could be something going on there. Theoretically, I would say maybe if they finished the 4 years of college, maybe it's less than 16%. This is just the card problem, right? You pick a card, if the probability that it's a heart is 1/4, but the next card, if I know you have a heart, the next card, that probability is not going to be 1/4 anymore. So that's what they were asking you in this problem. Do you think it would be different than 16%? Yes, I think so. I think that's a reasonable conclusion. There's a dependence there. So that's what 29 was all about. Now let's go take a look at 30. All right? Almost 90%. Oh yeah, they're independent. How do you know? Well, we have a formula that we use. If we know two events are independent, then this formula works, right? We'll go the other direction. If this formula works, then they're independent. If this formula does not work, then the events were not independent. All right, let's take this through now. You found the probability of A for this was that 0.256. Okay? The probability of B was 0.31996. Now, from your tables, okay, you should have seen that the probability of both, so from the tables, you should have got, this is the 10,000 number over the 175,000 number. So from your tables, you should have realized this was 6%. So that's the correct answer. That is the probability of A and B. Well, question. Does that equal these two multiplied together? Which was what many of you did. You just blindly multiplied those together. And those of you who did got this to be what? 7%, right? So they are not. They do not equal each other. In this problem, they actually gave you the math to go prove one way or another if they were dependent or independent. You don't just assume it. You don't just say, oh, they're independent, let's go multiply them together. You can't. So in this problem, they were dependent because the formula didn't work. All right, let's go in over here what we're doing now. This is called a Venn diagram. It's just a tool that you can use to solve some of these probability problems. Sometimes it's a good idea to use it, other times you won't. But it's just something that you have at your disposal if these problems get kind of tough. Sometimes creating a Venn diagram will help. So this Venn diagram I want to know for this class, so this rectangle is our entire sample space. It's our entire class. Okay, I wanted to kind of find out the percentage of these different areas. B means you love basketball, and V means you love vegetables. All right? So I want to try to figure out the probability. So if I just ask this class, this is all I ask them. Hey, I wonder how many of you, what the probability is if I pick somebody in here that they will love basketball. So you've got a choice here. All right, Madison, how many people in this class love basketball?
13.
She's right. She's right. The answer is 13. If I just ask that question, am I asking anything about vegetables? No, I don't care about that circle of vegetables. Forget it is even there. Just look at the basketball circle. There, if I just ask you the question, hey, how many of you love basketball? There would be 13 hands that go up. So therefore, what's the probability someone's going to love basketball?
13 over 29.
And did you make that into a decimal?
Yeah, 0.45.
Okay, about 45% chance someone loves basketball. Okay, one of the cooler tricks that you can use, and it's really going to help you when you get down here into these ugly ones, is I like to shade the pictures. And when you shade the pictures, it's real easy to see what region we're talking about. So if I want to take a look at a Venn diagram and I want to know the probability that they love basketball, you just shade the basketball circle. So everywhere I see basketball, I shade that circle. I'm sure you've got this in your notes. We'll just go this as we go. Don't worry about them all right now. Just go as we go. And that's the 13, right? That's the 13 over 29. Okay, by the same logic, Mason, how many people in here love vegetables? 15. So what's the probability someone in here loves vegetables?
Well, I did it wrong, but...
Okay, but now it's going to be 15 over...
it's 52%.
Is that right, 52%?
Yeah.
So you got that right? This is important.
Around.
Okay. All right, so a little more than half. There's a 52% chance people in here love vegetables. All right, Kyle. I'm going to figure out their intersection. So all I have to do is multiply the 45% times the 52%. Correct? What is that? Put that in there real quick for me.
0.21 equal.
We have a formula for it, right? There's the formula. No! No! Now let's take a look at this thing. When did I say it was okay to use that formula? Do you know for sure that in this class there's an independence between loving vegetables and loving basketball? They sound kind of, they don't seem related in any way, shape, or form, but you just can't assume that. And actually in this problem, it's just like we did on 30. You can prove that one way or another. So when we multiplied these together, we got 21.81%. Well, from our Venn, what is the probability that they love both? How many people in here, if I said, how many people love basketball and vegetables, how many hands would go up? 8. So the correct answer here is 8 over 29. What does that equal? 0.2. So answer the question for me. Are these two events independent?
No.
No, they're not. We just proved that they're not. Because that little formula that you wanted to use, you threw it right into that formula, and it didn't equal what the actual results were. So guess what? If I know somebody in here loves basketball, the probability isn't 52% they love vegetables. It's different. There's some sort of weird relationship going on. I don't know, the girls like vegetables more. I don't know what it is, but there's something going on. Yeah.
So we're still talking about only in the long run.
Yeah, in the long run. These are all portions in the long run. But this is just our class, though.
Yeah.
So this isn't. This is what it is in here. So the correct answer here was the 8 over 29, or the 28%. Okay, so please don't just blindly go multiplying things unless you know they're independent. And in this problem, we could prove it one way or another.
So, but you can't draw the conclusion that loving basketball and loving vegetables are dependent, right?
For this class, it is.
Well, for this class,
Now, I can't infer that onto everyone in the world, but in this class we've shown that it is. There's a
But
dependence.
you can't just say they're dependent because they're only dependent in terms of this, the sample of this class.
Right, and is this a very good, did I draw a very good sample just by picking you guys? Is that a representative of the whole population? No, that's the whole last chapter stuff we were talking about. But for this class, there's a dependence going on. There's definitely a relationship there. Back to our drawings here. So the second one, if I just want to figure out for the probability of vegetables, we would just do the vegetable one. All right, now, if I'm trying to figure out the probability of both events occurring, now it's kind of easy to see on that one, but sometimes we're going to get into some harder ones, so this is kind of a nice little trick that I have here. All right, so we'll do both of these. Let's shade the region that's basketball. All right, so we shade that circle. Just like I did before. So I'm just shading the basketball region. Now, go shade the vegetable region, but we'll actually shade it going the other direction. So just for the vegetables, I'm going to shade that region. So which region is in both, is in common for both? Well, it's the region that has the double crosses. So that's how you can see real easy which region we're talking about. And like I said, when we get to some of these tougher ones down here, this is going to be a nice feature for you. Okay, well now I have to figure out the probability that somebody in here loves basketball or loves vegetables. I have a formula for that. Awesome. That's my formula that I learned. How do I find the union of two events? I just add those probabilities together. So I'm going to do that. So I'm going to add the probability for basketball. That's 13 over 29 plus. I'm going to add for the volleyball. That's 15 over 29. I get 28 over 29. And that's the number of people that love basketball or vegetables. Look at the Venn. If I ask you to raise your hand, how many people in here love basketball or vegetables? How many hands would go up? There would be 20 hands that go up. Does everybody see that? You folks in here, you love them. Only you guys out here don't love them. And I said or, right? So either one. If you love them both, great. If I said, hey, do you love basketball or vegetables? And you love them both, you'd be, yeah. But we didn't get the right answer using our fancy formula. Why not? What happened when I used our fancy formula?
You showed that in this case it's not independent.
It has nothing to do with independence at all. Do not get them confused. I'm off independence now. Yeah.
So by doing that, you are counting some people more than once.
Look, didn't I count? Who did I count more than once?
The people in the middle.
Didn't when I said, okay, here's all basketball, and then I said, okay, here's all vegetables. Did a certain region get counted twice? Now, why? Go back. Just why didn't this formula work? What was it about this formula that had to be true in order to use this formula?
It had to be an independent.
Nah.
Oh, it had to be dependent.
No. Okay, now he's confusing them. Okay, I remember I said this. It's so easy to do. It's so easy to confuse these two concepts. Okay, they were mutually exclusive. Remember, that's the mutually exclusive one. This is the one that uses mutually exclusive. Are these two events mutually exclusive?
No.
They are mutually exclusive. They're not mutually exclusive. I know! Remember what mutually exclusive means. Mutually exclusive means they can't happen at the same time. Are there any at the same time in this one? Are there people in here that love them both?
Yes.
So this is not mutually exclusive. If this was mutually exclusive, this would be a big fat 0, right? It's only if their intersection is 0. So these aren't mutually exclusive. You can't use that formula. Because if I use that formula, look what happens. I add the middle twice. That's why. We've got a new formula for you. It's called the general addition rule because it works every time. Go to your green sheets, page 5, I think. This is so important. This is one they gave you. Go find it on your green sheets. This is not one you have to remember.
So mutually exclusive events are dependent, but not mutually exclusive events can be either dependent
Yes.
or independent.
Yes. You just confused the heck out of me, but I think what you said is right. Does everybody find it? It's on the top of page, top of page 4. You'll find it. It's on the top of page 4. Now, this formula should kind of make sense to you. Here's what we're going to do. Okay, we're going to add both of the probabilities together, but then look what they do. They subtract the middle once. Didn't we add it twice? So if I take one of them away, okay, I will just be adding, so I'll be adding up to 13, I'll be adding up to 15, but take that 8 away because I added it twice, and I'm at the number that I should be. So that formula should kind of make sense to you. Okay? So in this particular problem, what we're really doing here is we'll add those up, but we'll subtract 8 out of 29, and that gets us to the 20 out of 29 that, is that right? No. 20 out of 29? Yeah. It's 30. 13, 15, minus 8. Yeah, minus 8. Okay? All right, so here's going to be your challenge. On some of the problems you're going to do tonight, they're word problems. Okay, they're not going to be a nice big Venn diagram for you. It's okay. Read a sentence and change those sentences to symbols. It might say, hey, the probability you love volleyball is 40%. Okay, but the probability of volleyball is equal to 0.4. So change that word to sentence. Then it'll say, hey, the probability of loving
Tacos.
tacos. Well, that's like 100%, isn't it? That's 80%. Okay? And then they'll tell you, like, and the probability of loving them both is, 50%. What's the probability that you love one or the other? So at this point, we write our formula. The probability of tacos or volleyball is the probability of tacos plus the probability of volleyball minus the probability of both. And just plug in the numbers as they fit. 0.8 plus 0.4 minus 0.5. Get your answer and write your sentence. Write that down. That's what I'm going to see on your paper a million times. Anytime you have a word problem, change the sentences into symbols and then go ahead and use that general addition rule if it's an OR problem. Now if they give you a Venn, it's a little easier to see. So if it is a Venn diagram, how do I see the OR region? Okay, well here's what we do. We do exactly what we did before. I'm going to shade the basketball region. Okay, shade it. Don't care about anything else. I'm just going to shade what is in the basketball region. Then it wants me to shade the volleyball region. Okay, shade the volleyball region. But now if it's an OR problem, here's my thinking. Anywhere I see shading, you're good. You're good, you're good, you're good. Anywhere I see shading, you're part of my party. Okay? I am a boy or a girl. Yep. Right? You meet any of them, you're good. Meet both of them, you're good. That's what we did over here, right? You could just add these three together. If you have a Venn, you don't have to worry about that subtract stuff. You can just add what you see. Okay, so if you have an or problem, shade them, and then anywhere you see shading, count that region. All right, so now they get a little trickier. Probability someone does not like basketball and they love vegetables. It kind of gives you a little headache just saying it. So if you don't see that region easily, let's just go to our charts here. Let's shade it to see what the heck region they're talking about. So the first thing I have to do is shade the region that is not basketball. Give it a try. I'm interested to see what you shade. So you have to shade everything that's not basketball. How would you shade that? I want to shade everything that's not basketball. Remember that little complement symbol, that little dash means not. So I want to shade everything that's not basketball. If I ask this question, who here doesn't like basketball? I would see how many hands? I see 16, right? So the region that's not basketball is everything outside of here. You see that? That's the region that's not basketball. Now let's shade the region that is vegetables. Okay, I just forget about everything else. I'm looking at my vegetable circle. So I want and, it has to be both. So what region are we talking about? It's the double region, right? That are in both, that are common to both. So that must be this 7. And that makes sense. Let me say this a different way. How many people in here don't like basketball, but they do like vegetables? You kind of see it that way, don't you? It means... All right, how about this guy? They love basketball, or they don't love vegetables. Shade that. Tell me how many you get. So this time we're loving basketball, or we're not loving vegetables. See if you can get the right shaded part. This one's a little harder. The shading really helps on this one. All right, loving basketball. That's this guy. Not loving vegetables. Okay, that's everything outside of the vegetable circle. And then it's an or problem, right? So anywhere I see shading, the you count. So I'd be on the outside, so it looks like the 9, the 5, and the 8 all count. What is that, 17, 22? 22 over 20. Okay. Tonight you'll be asked to create a couple of Venn diagrams. You're also just going to have word problems. If you're given a word problem, just change the words to symbols and use the proper formula, the general addition rule, plug them in the right plot. And then they get really dastardly on you. They could, in your word problem, I don't know if you have any like this tonight, but in your word problem, they could give you this one, and this one. Could you then solve for the one that's missing? So they can play with this formula in any number of ways. So when you read the question, half of the trick, when you read the question, is to figure out, oh, that's really the probability of A and B, and write that down.
Better.
Create this Venn diagram. Looking around, not thrilled. Question. What percentage should we have for this whole thing?
100.
1 or 100%, right? Many of you are breaking rule 3. If you add up those regions and you're getting more than 1, well then it also has to add up to 1. Ah. Brainstorming. You have a hint now. It's got to add up to 1. Lucky. Come on! Those of you who are struggling right now. Is there any region that I can fill out for sure that I know that I know is going to be right? What region can I put in here first? Which one? A and B, right? I know that's 0.2, don't I? That's the region that's it's both A and B. That's a 20% chance of that happening. Now here's what a lot of you did. Okay, I got that. Now I'm going to do that. Take a look at region A. How much do I have in region A right now? 60%, don't I? I like to equate these problems like you're inside of a box of popcorn. You got to eat your way out of the middle. That doesn't make sense. Anyway, so we start here. Always start in the middle. Okay, so we know that's 0.2. So how do I figure out what that must be? Well, the whole A has got to be 40%. So what must be over here? 20%. Now the whole B must be 30%, so what must be over here? 30. Whole B must be 50%, so what must be over here? You get that through subtraction. And don't forget now, the whole thing's got to add up to 1, rule number 3. So what's going to be left on the outside? 0.3? Do that right? Now, just so you know, Venn diagram should be, it's just the same thing as a 2x2 table. Okay, so fill in the regions of the 2x2 table. So each one of these 4 regions belongs in one of these. So when you see a 2x2 or a two-way table, we've done these before, it's the same thing as a Venn diagram. What's going to go right here with A and B? That's the 0.2. This one's going to be A but not B, so what region's in A but not B? It's that guy, isn't it? What region's not in A but it is in B? That's here. And which one is outside of B and outside of A? That's that guy over there. Yeah.
But you the 0.3 outside it.
Okay, well, what do I know that the entire sample space has got to be equal to? So the whole thing's got to be 1, right?
Yeah.
And I really only have 4 regions here I'm dealing with. If I add all those up, it's got to be 100% of you guys, right? So when I got these 3, that's 70%, so what's left is by the common rule. Okay. All right, a lot of stuff today. Really important. This is 3rd or 4th day in a row we've talked about this. Don't just, number 1, blindly multiply a couple of things together unless you know they're independent or not. But now you've got a couple of ways to determine independence. One of them is asking yourself that question. If I know what happened before, it's going to help me through what's next. Now you've actually got a mathematical way to prove it one way or the other. Okay, we came up with the general addition rule today. Make sure you're changing your word problems into symbols, write the formula, plug them in, and go from there.